continue. Let's sort of recap where we left off last time. So we were starting to introduce the concept of enzymes and how redox reactions in biological systems are under the control of these biological macromolecules. Their function is to provide a unique chemical microenvironment within which the reacting substances can come together and more efficiently react with each other, which then ultimately leads to a greater speed of reaction. We're going to talk a little bit about kinetics towards the end of this chapter. And for concepts that are going to come back later, I mentioned that enzymes are exceedingly able to very exquisitely control the manner in terms of three-dimensional orientation that the reactants come together and thereby determine what is going to be the ultimate three-dimensional shape of the molecules that result from those transformations, which, as we're going to learn again in more detail later, is critically important in biochemistry. So when a redox reaction is orchestrated by an enzyme in order to avoid altering the structure of the enzyme itself, enzymes that are redox enzymes carry what are known as coenzymes, which are just accessory molecules, also known as prosthetic groups, believe it or not. And these structures are the ones that undergo the actual oxidation and reduction functions of the enzyme. And we closed last time talking about the definitions of what are known as oxidizing and reducing agents. As the term implies, an oxidizing agent is the substance or agent that causes the oxidation of something else. And if something else is becoming oxidized by the actions of this agent, then the agent itself must become reduced. The converse would be a reducing agent, which it would be pretty much the exact opposite of that situation. By the term, a reducing agent induces the reduction of another species, therefore it becomes oxidized in the process. Why we have the two terms when we can pretty much just stick to one, depending on what we're talking about? Because again, it depends on the perspective from which you're looking at the transformation. In some cases, the substance that you're looking, studying, paying attention to is becoming oxidized, and therefore it's better to speak of the oxidizing agent that causes that oxidation. In some cases, the structure that we're paying attention to and studying and interested in is being reduced, so then we need to identify what's the reducing agent that causes the reduction of that substance. So when we're looking at biological systems, and we're going to expand on this when we start actually looking at chemical transformations in biochemistry, there are two primary pairs of redox coenzymes. They actually have to exist as a pair because one, the coenzyme can transform itself and be in what we call the oxidized state versus the reduced state, depending on the state of the reaction that is being carried out. So when you're comparing these redox coenzymes, depending on which direction the reaction you're looking at is going, is which of the pair of the two possible entities is reacting. Of each pair, one species we call the oxidized form of the coenzyme, and the second one is the reduced form of the coenzyme. So by looking at these two, how do you know which one is the reduced and which one is the oxidized one? So the first one is called NAD+, is one of the pair. The second one is NADH. The second one is FAD versus FADH2. Which one is the reduced one in each case?
NADH and FADH2.
And because?
They have a hydrogen, which means...
Correct. So the higher hydrogen content, in this case the H actually stands for hydrogen. There's one on this one and there's two on that one. The one that has the greater degree or content of hydrogen is the reduced form. The one that has less hydrogen is the oxidized form. So, depending on the reaction, the same enzyme can create or can affect an oxidation or a reduction depending on which one of the pair of the redox coenzyme it is carrying. So if it's carrying the NAD+, that's the oxidized form of the coenzyme, that coenzyme can accept hydrogen and be reduced in the process. If the coenzyme is being reduced, that means that the substrate that the enzyme is acting on is the one becoming oxidized. Okay? The converse would be if the enzyme is carrying, the same can be said about FAD. If the enzyme is carrying NADH or FADH2, the coenzyme can lose hydrogen and become oxidized in the process. Something needs to be there to trap, catch, gain those hydrogen atoms, and that's the substance that then becomes reduced in the process. So when you're looking at redox transformations in biological systems, you need to pay close attention in which direction the reaction is going and which of the coenzymes is being carried by the enzyme. If it starts with NAD versus NADH, that completely changes whether the reaction is going in an oxidation or a reduction direction. Okay? So again, as I've said, the member of each pair that has less hydrogen acts as an oxidizing agent because it itself is becoming reduced by accepting hydrogen. The exact opposite happens with the one that has more hydrogen. It is acting as a reducing agent because it's losing hydrogen and giving it to something else. That substance is becoming reduced. Okay? So these are the structures of NAD plus and NADH. And again, we're not going to ask you to recite the entire structure of the compound. But what we do want you to identify, and we've put it in this little red box up here, this is the actual portion of the structure that is directly involved in the redox transformation. So as you're going to see as we start going through biochemical pathways, biology is exceedingly complex, and it loves to use these very convoluted, very cumbersome, large structures for whatever reason, and then it turns out that only a little tidbit of that structure, only a little tip at one point, a couple of atoms out of several dozen or so atoms in the structure are actually involved in the transformation. So if you pay attention, on the top left piece of that entire structure, only at the atom that I'm going to use the little red pen on here, that's where the reaction is happening. So notice how that carbon has only one hydrogen on the left, whereas on the right it has two. The structure has gained a hydrogen atom. Only on that position. The entirety of the remainder of the structure remains intact. Now it's NAD plus because it turns out that the nitrogen has a positive formal charge. If you count the number of bonds on nitrogen and divide electrons, as we learned in the first half of the course, this nitrogen with 4 bonds gives it a positive formal charge. When this gains a hydrogen atom plus 2 electrons with it, it turns out that then changes the electronic structure of the compound from being an aromatic ring that contains the nitrogen embedded within it. Now the structure has changed because of the gain of that hydrogen, and now the charge disappears. And if you notice, there's been a gain of a hydrogen atom in this specific position. Okay, so this is that the NAD plus NADH pair, and depending on whether a reduction or oxidation is happening is which one of the two coenzymes is going to be utilized. So for example, one reaction that we're going to study when we talk about glycolysis is the conversion of pyruvate to lactate. So these little double arrows going in one direction and another, we're going to start talking about what this means in a couple of lectures. This, in fact, means that the reaction is reversible. It can go in one direction or the other depending on the needs of the cell, depending on the environment, depending on how much of the reactants and or products are present in the transformation. So when you metabolize glucose under conditions of limited oxygen availability, which is what happens when you're doing very strenuous exercise, and you may ask yourself, well, how can there be low oxygen availability if I'm exercising really, vigorously and I'm breathing like crazy? Well, because it turns out that the rate at which you're breathing can still not keep up with the rate at which the sugars are being burned to provide the energy for the exercise that you're undergoing. So when that happens, the glucose gets broken down to pyruvate, and the energy that's contained in that glucose is extracted in the process by mechanisms we're going to learn a little bit later. But then, in order to be able to keep that glycolytic pathway going at the rate that it needs, that glucose needs to be metabolized, it turns out that the only way to make that happen is for pyruvate, which is the end product of glycolysis, to be reduced to lactate. And this is lactate, i.e. lactic acid that you may have heard about that accumulates when you're doing heavy-duty exercise. Well, the pyruvate is reduced to lactate, something needs to be oxidized, right? So the NADH is the one that is oxidized and it becomes NAD+. So in this case, the top reaction is going backwards, going from right to left. The NADH becomes NAD+, and in doing so, the pyruvate becomes lactate. And this is the substance that accumulates in your bodily fluids, being produced by the muscle, and ultimately irritates your muscle and is associated with the muscle aches and pains that are associated with heavy-duty exercise. It's the accumulation of lactate, which comes from the lactic acid. So the second pair is FAD, FADH2. On the left is the oxidized form. And here again in the red box, you can identify, if you compare to that same region on the structure on the right, again, notice the similarities between portions of the structure. If I go back to NAD+, this whole piece here, including up to the two phosphates, is pretty much the same. Beyond that point is where the structure is a little bit different. But if you then pay attention to the red box on the left and you compare it to that same region on the right, you will notice that there's been a reorganization of the electrons and the bonds, and particularly, let me change the color to something a little bit brighter. The green is a little bit better. So if you compare that part to this part, you'll notice that there are now, on this nitrogen, I don't like that one. Sorry. There are now, if you compare these two nitrogens with these two nitrogens, 2 hydrogen atoms have been gained by the structure. Okay? So again, as I've said from the beginning, and we talked about this last time as well, part of the skills that you need to develop in this course, continue to develop in this course, is paying attention to detail, right? So if you're given a structure and there's a transformation that you know has happened, well, I need to scan the structure and try to figure out what changed, how did it change, and what type of process are we talking about, right? So this is the gain of hydrogen by an organic structure. This is a redox transformation, right? And the one on the left is in the more oxidized state. The one on the right is in the more reduced state because it has more hydrogen, excuse me. So here is another example of a transformation involving this pair. In this case is the conversion of succinate to fumarate. This is one of the reactions in the Krebs cycle, or also known as the citric acid cycle, which we're going to be learning again at some point later in the semester when we start talking about metabolism. So if you look at the structure, succinate becomes oxidized to fumarate. How do I know that that's just by looking at it? Never mind the redox coenzyme. Typically, well, the moment you see the redox coenzymes in the reaction, you know for sure this is a redox transformation. The question is, what got oxidized but what got reduced? Well, you can already establish that the coenzyme got reduced because it gained hydrogen. So therefore, the succinate must have gotten oxidized. So how do you know that it was oxidized, and what part of the structure tells you that? Yes?
The double bond in the middle.
So how do I know that that, relative to the other piece in the previous structure, is an oxidized version?
Well, when you have carbon, it takes away slots for hydrogen.
So how many hydrogens are on this carbon?
2.
There's 2 hydrogens here, and there's 2 hydrogens here, right? Because carbon forms 4 bonds. If I look at these 2 carbons, the double bond is 2 bonds. The bonds to the other entities is 2 additional bonds, right? 1 from each carbon. So this only has 1 hydrogen. Pen is not working here. And this only has 1 hydrogen. Oops, pen is not working down here. But anyway, there's 1 hydrogen here and 1 hydrogen there. So notice how the structure has lost from what was 4 hydrogens over here, it's now only 2. But where do they go? Well, they're here, right? they were transferred to the FAD, and it became FADH2. So because the FAD was reduced to FADH2, something was oxidized. Well, succinate was oxidized to fumarate. Okay, so these are things that when you're given a transformation, you need to be able to look at the reaction and say what was reduced, what was oxidized, right? So technically, FAD is acting as the oxidizing agent, right, that is causing the oxidation of this one. Well, it in the process becomes reduced. Okay? All right, so this is terminology that you need to be familiar with. So, as we're going to see, we're going to be looking at transformations that are multi-step. And in some cases, we're going to be seeing a sequence of reactions of all different kinds that we've been talking about. You need to be able to look at the reactions and identify what's happening, which ones are redox, which ones are not redox. And if they are redox, then identify what's the species that was oxidized, what's the species that was reduced, and so on and so forth. So here's a little example, a little snippet of a much longer pathway, which is called beta oxidation, which is one of the steps in the metabolism of fatty acids. Fats and oils get metabolized. Ultimately, this is just a little portion here. And we're going to be looking at the whole thing a little bit later. But for example, if you look at this first transformation, this is very similar to the one we saw here with succinate becoming fumarate. A fully saturated alkane carbon-carbon type bond becomes a saturated alkene type bond. So this is an oxidation reaction. So you can see that as this structure here, this thioester, becomes oxidized, or something must have been reduced. Well, it was the FAD that became FADH2. Because we typically do not focus our attention on the coenzymes. They're part of the enzymatic reaction. But what we are more interested in is the actual organic substrate that's being transformed, from this large fatty acid that provides fuel to something smaller. And as we break it down, we extract the fuel. You need to pay attention to the substrate as to what happens. So again, a single carbon-carbon bond becoming a double carbon-carbon bond is an oxidation process. Now notice, water enters into the equation. Water is very abundant in biological systems, so it's kind of a given that it's everywhere. We don't necessarily explicitly and very, very in your face show it as one of the reactants. We can put it over the arrow and say, oh, water molecule comes in. But then observe, what was HOH, as we've been saying, becomes incorporated. It adds across the double bonds. This is an addition reaction, also known as a hydration process, because the water becomes incorporated, right? You can also call it a synthesis or composition reaction, right? Technically, these redox transformations are double replacement, right? Ish, because things are going back and forth. And then here's another oxidation process. So just by looking at the presence of the coenzyme, it has to be a redox transformation. But then what was oxidized, what was reduced is the question, right? Well, I've already told you this is an oxidation. Oxidation with respect to the substrate, right? What's being oxidized is the alcohol, right? And it's becoming a ketone, right? If you pay attention to there's a hydrogen here. This pen is acting up again. Come on, I don't have time for this. Seriously? Was working fine. Hold on, let me do this and see if that does it. They've told me that if I shut this off, it works. Let's see if that's true. Of course, now I've screwed up with the clicker application. Now it should be fine. All right. Nope. Oh, there it is. So hydrogen here, and there's a hydrogen here, right? The pen isn't cooperating with me. I'll write it over here. Let me turn the light on for those of you who are in the back. You're going to understand what this means, and in fact, I'm going to draw this like this. So there's a hydrogen here, right? And there's a hydrogen here, right? And then if you notice, this ultimately becomes right? So the entirety of the hydrogen on this carbon has been, on this piece of the structure has been lost. So this here must imply that this is an oxidation process, right? So if that's an oxidation process, something has become reduced. Well, what was reduced? Well, the NAD plus became NADH, okay? And that's the reduction part of, I'll turn this on, I guess, but you can see it. Is that light okay? Can you still see it? All right, so for organic reactions of the kind we're going to be looking at in biochemistry, again, what you really need to focus on is the hydrogen versus oxygen, or a combination of the two, how those change. Again, if hydrogen is gained, that's reduction. If hydrogen is lost, that's oxidation. We haven't seen examples of oxygen being gained, but here, for example, we gained a bond to oxygen. Gaining bonds to oxygen, it went from carbon, oxygen single bond over here to a carbon-oxygen double bond. The total oxygen content didn't change, but the number of bonds to oxygen went up. That is also technically an oxidation process. So both things happen simultaneously in this process. We lost hydrogen, we gained bond to oxygens. Both of those things go in tune with an oxidation process. Now, when we're looking at inorganic transformations, of which they also exist in biological systems, although they're less frequent, typically the way that we then establish that there's been a redox process, that we've already done these types of examples, is by a net gain or loss of electrons. Electrons are being transferred from one species to the next. So in this case, we established that, let me see if this is working down here, that this is technically copper 2 and 2 chlorides, right? And then this is zinc metal. That becomes copper metal. And zinc chloride is zinc 2 plus 2 chlorides. So what did we call this? That is present both before and after. These are spectator ions, right? So this does not participate in the transformation. Only the copper 2 reacting with the zinc to produce copper metal and zinc 2 is the actual reaction. In this case, this is the oxidation, right? And then the copper 2 becoming copper metal, that's the reduction. My apologies that the pen isn't working. I'm going to have to go yell at somebody at some point soon. All right. So this is what I've already said, that when we're talking about organic transformations, it's typically looking for changes in oxygen versus hydrogen content. And this is what we've already said, right? We talked about this before. This is sort of a review slide. Again, if you dissect that reaction that's on the previous slide, and you then observe that the chlorides are present both before and after, right? This is a spectator, this is a spectator. And then the true transformations are this as the reduction, and then this one as the oxidation. Okay? Everybody's with me? All right. And we've already talked about this. This is sort of a review session here, right? So again, this is what we call the net Ionic equation. The true reaction is between zinc metal and copper 2 ions to then produce copper metal and zinc 2 ions. And you can identify the oxidation process, which up here will be this one, right? How the zinc loses its 2 electrons. Well, those 2 electrons then need to be gained by somebody. Well, the copper 2 picks them up and ultimately produces the copper metal. If you add up these 2 reactions, notice anything that appears on both left and right, this and this, they're going to cancel each other out. And then if you add this up, you're going to end up with copper 2 plus zinc metal making copper metal plus zinc 2, which is the reaction that's on the top here as the net reaction. Again, this here is the reduction process. Okay, everybody's with me? So back to the terminology, because zinc, its electrons, zinc metal, its electrons reduce the copper 2, we could say that zinc is the reducing agent, right? But of course, in the process, it becomes oxidized. Yes? So you could also say that copper 2 is causing the oxidation of zinc metal because it is trapping those electrons that are released by the zinc metal. So technically copper 2 is the oxidizing agent that's causing the oxidation of the zinc metal. So again, it depends on the perspective, right? But you need to be very clear as to what those terms are, right? And then just, again, by identifying what's oxidized, what's reduced, just by following the flow of the electrons. But never mind that. If you're just given the top reaction, no electrons are visible, you're noticing that copper, its oxidation state goes from being positive to being 0, so it goes down, right? So that means it's been reduced. The zinc goes from 0, which is the elemental zinc, to becoming a 2+ ion. Its oxidation state went up. So it must have been oxidized in the process. Okay? All right. So these redox reactions, as we're going to see later, they're exceedingly important in metabolism in general. We just give you a little snapshot of some pathways that are critically important to sustain our daily activities that involve these types of reactions at some step or another in the pathway. But it turns out there's many more implications of these types of transformations in sustaining life. So our red blood cells, of which we have about 25 trillion that are flowing in our blood system at any moment in time, they are traveling through the body, being exposed to all sorts of different things. They pass through the lungs where they become oxygenated. Now, in order for the hemoglobin to be able to carry oxygen, the iron needs to be in an iron 2 oxidation state. Does somebody have a question? No? And only iron 2 bound to hemoglobin can carry oxygen. So it turns out that as part of our normal physiology, particularly when the hemoglobin is directly exposed to oxygen itself, the iron 2 that's on hemoglobin can become oxidized to iron 3. And the moment that happens, the oxygen carrying capacity of that hemoglobin is gone. It cannot carry oxygen any further. So that type of hemoglobin that is carrying iron 3 and is unable to bind to oxygen is known as a methemoglobin. And it can be caused by binding oxygen itself, as we're going to learn. It can actually, that reaction, that transformation of the oxidation of iron 2 to iron 3 can also be caused by a whole family of compounds known as peroxides. So peroxides are compounds that have OO single bonds. And OO single bonds are extremely unstable. The compounds that carry those bonds are collectively known as reactive oxygen species. They are produced in all sorts of places during primarily inflammatory or immune responses, but many exposures to many different things that enter into the circulation and ultimately end up in the liver for detoxification, they can ultimately cause the generation of these types of compounds. So the simplest of the peroxides is hydrogen peroxide, which you can go to CVS or Walgreens or whatever and buy a jar for like $1, right? Literally hydrogen peroxide, H2O2. But your body produces hydrogen peroxide among other peroxides. These are collectively known as reactive oxygen species. So when iron 2 is exposed to hydrogen peroxide, the iron 2 becomes iron 3, and then the electron that releases is picked up by hydrogen peroxide, a little bit of protons, which as we're going to learn is technically acid, that's always present in your biological fluids to a certain extent. That picks up that electron and the hydrogen peroxide is reduced to water. Okay? How do I know the hydrogen peroxide has been reduced? It's loss in oxygen, right? It goes from H2O2 to H2O. That's a reduction reaction, right? Loss in the content of oxygen. So, even at normal atmospheric pressure, any one of us in this room, about 3% at normal pressures of oxygen in the atmosphere, about 3% of our total hemoglobin concentration is in fact existing in the form of methemoglobin. So 97% of our hemoglobin is always working fine. we have about 3% that is gone. It's there, but it's not operational. So there are, in fact, a variety of different pathological processes. Some are genetic, some are acquired, some are the result of an exposure to some toxin or some infectious agent, or in some cases we don't know what the issue is. It just happens to happen. But some processes can lead to a pathologically unregulated process that ultimately leads to an increase of that 3% to higher percentages. And once that number starts going up, well, again, that's compromising the ability of our blood to carry oxygen. So it's sort of like a pseudo-anemia type of a situation. The blood cells are there, they have the hemoglobin, but it's not operational, right? So the body goes to certain lengths to maintain that level of methemoglobin in that up to 3% or lower. So here is just showing, for example, oxygen itself being the cause of the situation and then the issue becoming unregulated. But for example, here's heme, which is what actually carries the iron. This becomes part of the larger entity, which is hemoglobin. We're going to talk about the structure of hemoglobin and all that a little bit later. So when the oxygen binds to the heme, to the iron in the heme, iron starts as iron 2. This is just a little plus trying to illustrate that it's iron 2. The moment the oxygen binds to the iron, technically the mere binding process causes a sort of an internal redox process. The iron, by merely binding that oxygen and latching onto it, technically becomes iron 3. Now, as long as when that oxygen is let go in the tissues, the oxygen takes with it the same 2 electrons that it put into the iron to make the bond, then nothing has happened. The normal dissociation returns the iron back to iron 2. But it turns out that to a certain percentage, typically 3% or less, as that iron dissociates from the iron 3, it takes away an electron, and then it leaves behind an iron 3. And at that point is when the hemoglobin becomes incapable of binding to the iron. Turns out O2- is actually a reactive oxygen species that can also then cause damage and all kinds of different things. But then there are several physiological mechanisms to reduce the iron 3 in methemoglobin back to iron 2. Here's one of several. So typically what happens is that the reduction of the iron 3 to iron 2 has to be coupled with another reaction that is a net oxidation process, such that as something else becomes oxidized, the iron 3 gets reduced back to iron 2. So because glucose is so abundant, it is one of the, in fact, the primary source of fuel for all cells in the body. We have boatloads of glucose in our blood that is available for these things. So we can expend a little bit of glucose for other things, which one of them is this restoration of the normal hemoglobin. So glucose, by the actions of an enzyme, glucose 6-phosphate dehydrogenase, we're going to learn about a pathway that's known as the pentose phosphate pathway, that converts glucose to this alternative compound. It turns out to be an ester. But this pathway takes a coenzyme that is called not NAD+, it's called NADP+. It's the cousin of NAD+, the difference is that it has an additional phosphate. Okay, we're going to see that a little bit later. But anyway, so the glucose becomes oxidized. Something needs to be reduced within the enzyme. Well, it's the coenzyme. The NADP+ becomes NADPH. So now, another enzyme that's called NADPH methemoglobin reductase now takes the NADPH, reoxidizes it back to NADP+. Well, something else needs to be reduced. What's reduced? The iron 3 becomes iron 2 in the process. So the coupling of these two reactions, the first one converts glucose to an oxidized version of glucose that can then be utilized for other things. That produces NADPH. The NADPH can then be reutilized to then, the real task at hand here is to take the iron 3 and reconvert it to iron 2, which the body needs in order to be able to carry oxygen. So this is one mechanism. So if something is wrong, if something is not working with, let's say, the glucose 6-phosphate dehydrogenase enzyme, then we can't generate the NADPH that is then needed to return the iron 3 to iron 2. So what happens? Methemoglobin goes up. Okay, so there are also a whole bunch of genetic disorders out there in which something's missing in one step that causes all kinds of problems in all kinds of other steps, right? So we're going to talk about here and there some genetic disorders related to enzyme deficiencies. If you have a glucose 6-phosphate dehydrogenase deficiency, which is a well-known disease, then you have major problems with oxygen delivery because you have much elevated levels of methemoglobin, and then that causes problems. So it's all about the redox reactions that are happening sort of in the internal parts of the enzyme involving these redox coenzymes, where you have to be able to look at these reactions and identify what's happening. Notice again, the alcohol becomes a carbonyl structure, right? And this is an oxidation process. Something was reduced. Well, what was it? NADP plus becomes NADPH. If iron 3 becomes iron 2, something had to have been oxidized. So it was the NADPH becoming NADP plus. Okay? All right, everybody's with me? Oh, it's not up? It's not up? Okay, hold on. Let's see. I'm going to have to close this whole thing. Just give me a moment. So change the channel to some random number, and then once it's up, change it back to 70, just so that it disconnects. What's going on? All right. That was weird. Okay, so we were here. All right. Okay? All right. So, Let's answer some questions. So, redox or non-redox? Okay? All right, and the answer is? This is not redox. This is a double replacement inorganic transformation. Those are non-redox. Okay, I mentioned earlier that the FAD, FADH2, NADH, whatever, they're double replacement-ish, but they're redox. Those are sort of more complicated reactions for the most part. Double replacement is non-redox. Okay? All right. This one. Okay? All right. And the answer is, this is a redox transformation, right? And how do I know that? There's pure elemental oxygen. This is what other kind of reaction? I don't think that we've used this term in here yet, but anybody have any ideas what's happening here? This is ethane combining with oxygen to produce CO2 and water. That's known as what type of reaction? It's a combustion reaction, right? Combustion reactions mean something is burning, right? Combustion reactions are by definition redox transformations, right? And in fact, the reaction of anything with oxygen is a redox transformation. What's the oxidizing agent? See if you can put 2 and 2 together. Oxygen, oxidizing agent. The oxygen is the oxidizing agent. When anything reacts with oxygen, oxygen is what's causing the oxidation of the substance, right? That's where the whole term comes from. So combustion is the reaction of something with oxygen. The substance is becoming oxidized. So carbon became oxidized. How do I know that? Because it went from being bound to hydrogen and now it's exclusively bound to oxygen in the form of CO2. Something must have gotten reduced. Well, what was reduced? The oxygen was reduced. It went from being O2 element to being combined with hydrogen. Notice how the oxygen gained hydrogen, right? It became reduced in the process. If you assign oxidation numbers, you will observe that oxygen went from being 0 to being -2 over here, right? Carbon went from -4 to +4, -4, and hydrogen did not change in any way, shape, or form. It's -1 here, and it's still -1 here. So the redox reaction is in fact between carbon and oxygen in this process. Carbon became oxidized, oxygen became reduced. Okay? All right. Which substance is reduced in this reaction? Okay? All right. And the answer is? So let's start. This is the reaction that we've already seen several times, right? So this is zinc metal. Can't write on here. Let's see. So this is copper 2. I'll do it on the board. So if you dissect that reaction, this is zinc plus copper 2 plus 2 chlorides producing zinc 2 plus 2 chlorides plus copper metal, right? So this is a spectator. So zinc becomes zinc 2. This is the oxidation. Copper 2 becomes copper metal. This is the reduction, right? So what was reduced was copper 2. Okay, copper 2. So B is the answer. Okay, not copper, copper 2. Those are two different things. Cu, just Cu is copper metal, and that has a 0 oxidation state. Cu2 plus is the ion, right? So they're completely different things. Again, paying attention to detail. Now this damn pen again. Ugh, seriously? All right. Breaths. Which one is the oxidizing agent in this reaction, or is this not a redox process? Copper 2 plus. Okay? Yes? All right. Oh, we've gained 2 more people. Okay, the answer is? The answer is oxygen. Anything that reacts with oxygen, oxygen is the oxidizing agent. Okay? You can take that one to the bank. Now, what is getting reduced? So the oxygen is getting reduced because it's the oxidizing agent. What is getting oxidized? So let's dissect this reaction. The first compound is nickel. What's the name of that compound? Nickel. Needs to give more information. No. Not disulfide. Nickel. Do you see two sulfurs? Do you see a 2 by the sulfur? No. Plus, that terminology does not apply to ionic compounds. This is a metal with a nonmetal, right? So nickel sulfide, but you're missing something. Where is nickel in the periodic table? This is a transition element, right? So you need to say more. It's nickel 2 sulfide, right? So this is nickel 2. The reason why I have to ask that question is because this is, you need to recognize this is nickel 2 plus. Paired with, let's put the 2 there, right? With this, which is sulfide, right? So it says nickel 2 sulfide. That reacts with oxygen. That then produces nickel 2 plus, again, with, I'm missing a 2 here. And then plus SO2. I'm going to put it here. Yes? So, what can you say about nickel 2? It's a spectator ion because it's here and it's here, right? So nickel 2 is not involved in this transformation. The reaction is between sulfide and oxygen, right? So sulfide became reduced, oxygen became reduced, right? Because it's the oxidizing agent. We can establish that in a moment. What's the oxidation state of oxygen over here on the left? 0 because it's a metal. It's an element. It's an element. Over here in SO2, how do you assign for a molecular compound? We can talk about 2 ways of doing it. One is drawing the full Lewis structure, dividing the electrons, etc. The alternative way is simply the most electronegative element. You assign the charge it would have if it were ionic. Oxygen is group 6, more electronegative than sulfur. It will be -2. Oxygen is -2. Yes? What's the oxidation state of sulfur? Well, then you have to establish that whatever the sulfur is, plus 2 times the -2, because each oxygen is -2, that has to add up to the charge on the structure or the molecule, which is 0. Doesn't have a charge. It's not an ion, it's not sulfite, it's sulfur dioxide, neutral, no charged molecule, right? So what's the charge on sulfur? What's the oxidation state of sulfur? +4. So notice it went from a -2 oxidation state to +4. What happened to the sulfur? The number went up, right? From being negative to being positive. Sulfur was oxidized. Oxygen was reduced. How do I know? It went from 0 to -2, right? So this is, you can also see it here in oxide, but even in this compound. Oxygen was reduced. Sulfide, not sulfur, but sulfide, was oxidized to sulfur dioxide. Okay? If you follow the oxidation numbers, you can see it. Yes? So again, if you see oxygen in a reaction, elemental oxygen, it's the oxidizing agent. That's it. Right? You can take that one to the bank. All right. Did somebody needs this? You want me to turn this on again? No? Kind of heard a little scream there, no? All right. All right, so there are a series of chemical transformations that we need to talk about that have particular names because of the outcome, because of the visual outcome of the process. And amongst these reactions is what are known as precipitation reactions. And as the name implies, these are reactions in which an insoluble solid suddenly appears and precipitates, crashes out of a solution when 2 solutions are mixed. Now it turns out they are double replacement and therefore non-redox transformations. And the reason why the insoluble solid suddenly forms is because when you mix the two solutions, two ions suddenly find each other at a concentration that exceeds, or at a ratio that exceeds their solubility as an ionic compound. Therefore, the substance will crash out of solution, and we call that a precipitate. So we're not going to have you memorize this table, which is here. This is what our, if you go and take chemistry on North Campus, you will have to know this backwards and forwards, but we don't do that here, because this is information that's out there. Okay? So what we call the solubility rules. So there's a series of predictions that can be made about ionic compounds in terms of whether they're highly soluble or they're not soluble much or they're not soluble at all in water. This is an aqueous systems. So for just a brief, I'll walk you through one or two of them, but we're not going to go through the whole thing. So for example, in terms of salts that are soluble, all salts coming from group 1 metals, sodium, potassium, lithium, etc., all of them are soluble. It doesn't matter what the anion is. Lithium, sodium, potassium, chloride, nitrate, sulfate, carbonate, whatever you want. They're soluble because that's how it is. Same thing happens with ammonium. So this is talking about cations. You can also look at it from the perspective of certain anions. So all nitrates, all bicarbonates are soluble. So if you're given some random salt, magnesium bicarbonate, is that going to be soluble? Well, yes, because it's a bicarbonate. It's going to dissolve in water. You can go the opposite end. There's a series of salts that are insoluble. So for example, carbonates are generally insoluble. The exception, of course, is group 1 and ammonium, right? Oxides, sulfides, hydroxides, oxalates are largely insoluble with some exceptions, right? So why do we care about this? Well, because it turns out that phosphate is an exceedingly important ion in bodily fluids, and phosphates are generally insoluble. And we know that because otherwise our skeleton would be dissolved as we speak, right? Our skeleton is largely composed of calcium phosphates in different proportions of different ratios of calcium and phosphate, among other things. But phosphates are highly insoluble. That's a very important property of phosphates. Otherwise, again, our bones would be not what they are. Now, we're going to get to the connection with the phosphate in a moment. So we can speak of, just as we did with redox transformations, of these net ionic equations when we're speaking of these types of reactions by mere knowledge of the solubility rules and identifying that whenever you mix two ions that are incompatible, a precipitate will happen. So for example, let me go back to this one. Halides are generally soluble, except those of silver 1, lead 2, and some type of mercury ion, technically mercury 1, because notice it's Hg2, 2+. But never mind mercury. Let's pay attention to this one. Silver 1. So if you mix a solution that contains silver 1 ions in soluble form, for example, mixing them with nitrate, silver nitrate is soluble. Why? Because all nitrates are soluble, including silver. So if you have a solution of silver nitrate in which the silver is perfectly soluble, and you mix that with a solution of calcium chloride has exceedingly high solubility. If you mix those two solutions together, suddenly a precipitate will form the moment the silver ions find the chloride ions. That's going to form the precipitate. So the calcium in the presence of nitrate, nothing happens because calcium nitrate is perfectly soluble, but silver chloride is not. So the moment those ions find each other, they precipitate based on the solubility rules. So this is why this is important, because we have several physiologically relevant examples of these precipitation reactions that can lead to disease. Okay? So amongst the most harmful are calcium phosphate deposits. So your body goes to great lengths through the interactions of both the kidneys and the parathyroid gland that produces parathyroid hormone, whose main function is to maintain calcium levels within an acceptable range. Because the moment your calcium and or phosphate concentrations in your blood are off of what they should be, and suddenly calcium ions find phosphate ions at a ratio that's higher than allows for solubility, a precipitate will form. So, in your bodily fluids, calcium and phosphate have to be very well controlled to avoid the increase in calcium or the increase in phosphate, or a combination of the two, because the moment there's too much calcium or too much phosphate, or they both go up, suddenly you start getting calcium phosphate deposits in places where they shouldn't be. And what is the consequence of this? You can block blood vessels that can lead to ischemia, that can lead to death of the tissue. You can have strokes, you can have heart attacks, you can have all kinds of problems, right? So anytime you have hypercalcemia, hyperphosphatemia, or any combination, or you have kidney disease, you have parathyroid disease in which your calcium and or your phosphate, vitamin D can also play a role in that. If you don't know, vitamin D is important in controlling calcium absorption from the gut. So if you have vitamin D issues, whether it's the vitamin itself or receptors for the vitamin, all kinds of issues related to vitamin D metabolism, the bottom line, any changes in calcium and or phosphate can lead to these precipitates. So we also have several other diseases related to abnormal deposits of insoluble compounds, and these are typically ionic compounds that suddenly appear in places where they shouldn't be. So two notorious diseases are gout and pseudo-gout. And the gout is the main disease that is well known and has been established for a long time. And suddenly this other disease appeared, whose appearance in terms of clinical presentation with severe joint pain and inflammation and all kinds of issues appeared. And then it turns out that it wasn't gout, it was something else. Well, they called it pseudo-gout, for lack of coming up with a more creative name. So what happens with these diseases, and you have these abnormal deposits of these insoluble ionic compounds, and then for whatever reason, in some cases it's not clear why, they tend to accumulate in the joints and in certain connective tissues, and when doing so they cause all sorts of problems, and they can, when they deposit in these places, they cause severe pain and severe inflammation. So it turns out that the culprit in gout is a compound known as sodium urate, urate coming from uric acid. And uric acid is associated with certain foodstuffs that when you don't properly metabolize them, or they accumulate in certain weird ways that, again, not entirely clear. It's a complex process. There's a genetic component, there's an environmental component, there's a dietary component, there's a metabolic component. But ultimately, you get these sodium urate crystals that start depositing in places, particularly in the joints, and that leads to the disease called gout. Pseudo-gout is a completely different compound. It's a calcium pyrophosphate, also known as calcium diphosphate, again related to calcium phosphate. Bone is a combination of calcium phosphates in different forms, including pyrophosphate, also known as diphosphate. These are highly insoluble compounds, and then they start precipitating in places, causing all sorts of problems. There's another compound that can precipitate, again, as a combination of different types of contributors, which is calcium oxalate is another one. And it turns out that about 80% of kidney stones in the population are the result of calcium oxalate appearing in the general urinary tract, typically within the kidney itself, but they can actually form within the ureters and even within the bladder and all kinds of things. And it's more dangerous when they form within the kidneys, because then they can obstruct the ureter, the ureter, and then do backflow, and that can be all kinds of problems. But even when they form in the bladder, then if they're small enough, they go down into the urethra, but then they get stuck, and then it's a whole mess with kidney stones. So it has to do with the acid-base balance of the urine, and as I said, it's a complex process, but our body produces some oxalate that ends up in the urine, and then the dietary calcium that ends up in the urine as well, and as we're excreting urine, can produce the perfect cocktail that these things start precipitating. And then in terms of sources of oxalate, this is common in many, many foods that are out there, but particularly nuts and fruits and vegetables. So again, these things are everywhere, right? So it's not going to stop eating things just to avoid these things. And again, there's a genetic component. It's a complex process. So the interesting piece is that you can actually identify the different types of substances by looking into the microscope. So patients who are appearing with signs and symptoms that resemble gout and pseudo-gout, because those are very similar, the way to establish the diagnosis is by, it's a tragic situation. The patient, as in pain as they are, the doctor, this is typically done by a rheumatologist, they have to inject a needle into the joint that is excruciatingly painful, and on top of that they have to stick a needle in it. Take a little bit of sample of synovial fluid, and then you just look under the microscope. If they're very fine needles, the diagnosis is gout. This is sodium urate. If they're more like rhombic type shapes, not needle-like, then the diagnosis is pseudo-gout. Okay? And then, of course, in the case, this has nothing to do with kidney stones, because this is in the kidneys, the other one's in the joints, right? But you can actually identify if, depending on the size of the crystals, in some cases the patient will pass them into their urine, and you can actually take a urine sample and observe them. In some cases you have to stick a needle through the pelvis over here and go into the bladder and take a sample. On the other side you have to go through the back and go into the kidneys. If the stones are large enough, they can be seen through ultrasound. So there's different ways, but anyway, you can see, again, under the microscope is one way, before you start getting all invasive, is looking at the urine of the patient, and in many cases you will be able to identify these little calcium oxalate crystals that are precipitates that form, right, and are the culprits of the disease. All right, so again, just to kind of wrap this up, this discussion, so why do we care about all of these things that we've been talking about up to this point? So chemical transformations, and we've only started, once we get into biochemistry, you're going to see that the multitude of transformations we're going to be studying, they're responsible for everything that's alive, right? And when you're in health versus disease, there's changes in the chemical reactions that happen in your body when you're healthy and when you're ill. So every process that is responsible for sustaining life is a chemical transformation of some. So we still have about 10 minutes, so we're not leaving yet. Like I said, we're almost wrapping up with this section. That's what I meant. So this is the connection here, the important connection. Disease, what becomes manifest as macroscopic disease that you can see and feel and diagnose, is ultimately, if you go down and down and down, to zooming in and as far as you can go, it's in one way or another directly the result of some derangement in a chemical transformation. Okay? So this is why we have diagnostic tests that will allow us to determine, or try to determine, what is the chemical transformation that has gone wrong and why, so that then we can do a therapeutic intervention. Pharmaceuticals are chemicals that enter your body and interfere with a chemical process, and if something's wrong with that chemical process, the whole purpose of that chemical is to interfere with what's not right to put it back on track in the right direction. So in other cases, the pharmaceuticals are simply meant to target something that is irreversibly wrong, like things with cancer and things of the sort. And it's just a matter of just stopping that at all costs, right? Sometimes we're successful, sometimes we're not successful. So when we look at environmental disasters and many other public health emergencies, many of them have a basis in chemical transformations, oil spills and environmental exposures of all kinds of different chemicals that are out there. Understanding the chemistry behind what's the exposure and what happened is important. So again, all of these issues, resolving them in particular, requires knowledge of chemical reactions in one way or another. All right, let's do a little overview of the next section. So this is a critically important section as well, because this then allows us to understand a little bit more of the mechanics of chemical reactions. And we need to start talking about the concept of reversibility. I started to allude to that in some of the reactions that we saw a little bit earlier. So it turns out that if you look in nature, pretty much every chemical transformation to some extent will have a certain degree of reversibility. What that means is that as the reactants are being consumed, and their concentration starts going down and down and down as they start disappearing and reacting with each other, that ultimately causes the products that are forming to themselves interact with themselves, with each other, and ultimately actually return the reaction back towards the reactants. And what ultimately ends up happening is that as the reactants are moving forward and producing products at a particular rate or speed, the products start coming back towards reactants at a rate that starts at 0 because initially there's no products, but ultimately goes up. And ultimately what happens is that there's a constant ratio of reactants and products is established, and the reaction reaches what is known as chemical equilibrium. Okay? And it's a reversible process, it's a dynamic process. As a certain number of reactants become products, at the same time, a certain number of products become reactants, the net result is no change. But it's a dynamic process. It's not that it suddenly stops. It's just that some of this goes this way, some of that goes this back the other way, and you see no net change. We'll talk about that in more detail. So the extent to which reversibility happens, meaning how far the reaction goes to the left versus staying towards the right, goes to the right versus staying towards the left, just say that backwards, depends on this relative stability of the products versus the reactants, as well as the net, what we call chemical energy content of reactants versus products. So we're going to define these terms as we start this discussion. And then the last piece of this section that we're starting now, and then, mind you, we're just starting because we are on slide 50 of 136, right? Just FYI. The last piece of this section that starts now is talking about rates of chemical reactions, i.e. kinetics, how fast or slow a reaction goes. So it depends on several factors that have nothing to do with the stability of reactants or products. It actually has to do with temperature, how hot or cold you're carrying out the process, and how many of the reactants you have present, right? So we're going to talk about catalysts, which are most notorious in biological systems. We've already started to talk about enzymes. Enzymes are biological catalysts. Turns out catalysts also can be non-enzymatic. They can work perfectly fine in laboratory reactions. They have no role as catalysts in biological systems. There are many catalysts that can be created for laboratory work. We'll do some examples. And we're going to explore the importance of these catalysts in the process. And then again, we're going to start talking about these energy and rate considerations. So I think we can leave it there. And we'll continue, not tomorrow. Again, this is in place of tomorrow. We will continue on Thursday at 11.
filled out before I come to lunch. So not like you have questions on those questions, but in the notebook itself.
You can get, again, I think that the guidelines are posted. You can get a little creative. The more information you have in your notebook, the better it is because everything's in there in one place. Yeah, I mean, in terms of the procedure, we don't expect you to recite the entire procedure. You can use bullet points, summary points, however, whatever's going to help you. Use that. I mean, the whole point of the lab notebook is that when it comes to the procedure, you should be able to use the notebook as the guide to do the experiment. So however you want to write it, that when you're referring to it, you understand what needs to be done without having to every single time go back to the entire manual.
Okay.
But then it needs to be organized in a certain way that if anyone is going into that notebook, this is the whole point of a scientific notebook. You know, when you leave a lab and you're done and you graduate or you retire and all that work is left behind, some young person comes 10 years later, oh, let me look at this notebook that's connected. Everything should be there and they should be able to do and reproduce everything that you've done and all the information should be there for them. That's the whole point of a scientific notebook.
So it's more flexible, as long as you have the information, flexible how
Correct.
you want. Okay,
Yeah, yeah.
awesome. Thank you.
Yep. Yes, sir.
So with a patient with gout and Solubility, how would you treat that patient?
It's gout. There's different medications that are particular for the two because they come from different sources. In the case of gout, typically the underlying issue is the high levels of uric acid, so that has to be addressed. And it depends on whether the patient comes in with an acute gouty attack or not is the approach that is taken. So there's different medications, typically anti-inflammatories and things of the sort, but there are specific drugs that target the high uric acids as well, and it works with the kidneys and whatever. So it depends on the presentation. Sure. Yes.
Will you have office hours?
I will.
Okay.
I will be in my office as usual, 1 to 3.
And then, will there be a tutor this semester?
There is. I just got the information. I'm going to post it on Blackboard, and I'll send an announcement.
Would it be this week that she be in?
I believe so. Well, I haven't seen the schedule when she's there, but I know that we have one, and then she's on the schedule. I just don't know when.
And then the other question would be, because the last few classes you've had, you didn't have those questions, as many questions as you did today.
Right.
Is that going to count more against me?
No, those are worth 1 point each.
Okay.
It's like nothing.
Okay.
Believe me, it's nothing.
No, I know. I just stress because, like, as you
Yeah.
know, I try to get 100 on everything.
Oh, I know. Yeah, but believe me.
This is the first time I've actually done something stupid like that. I've been up since 6:30 this morning.
Yeah. No worries. I can assure you, missing one or even 2 classes is fine.
Okay. Thank you so much.
Sure, my pleasure.
And I will see you tomorrow.
You see me tomorrow. Yep.
Thank you.
I
Yes.
just wanted to clarify. So for the comp stuff, we're only showing up if there's a quiz.
If there's a quiz or there's an announcement like for today that we have a particular event scheduled.
Okay.
If I put a calendar on Blackboard, when you go into the course materials, the first thing that appears now is the course calendar. If you open that, you'll see that some days says open schedule, which including today. So open schedule means that there's nothing scheduled as of now.
Great.
But if we approach and we feel that we want to schedule something, we will announce, with reasonable notice to let everybody know that we're going to convene this day for this reason, and then we'll just do it. But if you don't hear anything, then the assumption is that we're not having anything.
Okay, great.
Unless it's scheduled, like the quizzes are scheduled. They're on there. You'll see this day is the quiz 1, this day is quiz 2. Otherwise, if it says open, if you don't hear anything, then assume we don't have anything.
Okay, thank you.
Yep. Hey there.
I have a question regarding to Orgo.
Yeah, of course.
I'm having trouble with Wiley Plus.
Okay.
It says that I purchased it and everything.
Yeah.
Did everything, but I don't know.
Where to find the book?
Yeah,
Well,
then it says you currently have no active courses. It's giving me.
You have to link to the course. So in the syllabus, or I think I sent in that first email.
Yeah,
there's a flyer. I don't think it's in there. Oh, it is in there.
Yeah, it's this.
This
right
is
here.
yeah. You have to go. You have to click on that, or even once you're in it, you have to find the course. So find your course, and then you're going to enter that number 743. The whole thing, yeah. Whatever it was. 743633. So just exactly. And then hit on that. So there's the course.
And then for the assignment, it says.
So there's no assignment. All the assignments are going to largely be as we've been doing. I post them.
So I think I have it pulled up. Yeah, so this is it, right?
That's the assignment.
So,
So,
like,
you're going to
1
print
point-
it.
Yeah.
So this is from the end of chapter, from the textbook. That's what that means. So you have to have access to the textbook, and then you have to go to the end of chapter problems. So if you go to course materials, let's see if that's where it is. No, down here, downloadable e-textbook. That's where it is. Yeah, go ahead.
Do I have to? I thought I already like purchased it.
Yeah, you did.
Yeah,
so
I
you
will.
shouldn't hit continue and see what happens. So you should have created a bookshelf account,
Yeah, I think I have one already for. Here we go.
and it should bring you at no cost because accessing Wiley Plus gives you access to the textbook. Okay, so I need to contact the Wiley Plus people
Yeah, I don't know.
because you should have access to the textbook.
Is it just because like I can't down? Is it just because for to download it I have to pay more, or can I like?
No. You should have. Well, you can likely download it, but it's going to be an electronic book, which is what.
Yeah, or it says see readings and resources. Is that
Hit that and see what happens.
so? Like, if I go to. Yeah, this is what I was at earlier. This isn't it, right?
But that's not the textbook.
Yeah, that's not it. So I need a.
No, yeah, you need the textbook. So let me contact. I saw exactly what you did. So I'll contact Wiley. What I'll do, here's what I'll do. I will post, because I have the book electronically, I will PDF those sections of the end of the chapter, and I'll post them on Blackboard until this is all resolved, so everybody has it just in case. And then I'll contact them to let them know exactly what's going on.
Okay, thank you.
All right, stay tuned. So I haven't heard. You may want to hook up. Ask with some of your classmates because I know other people have submitted the assignment, so they must have accessed it somehow.
Yeah.
So I don't know what the disconnect is with you, but I'll find out. But maybe we're clicking on something that's not what you should be clicking, and maybe that's why it's not working. So again, I'll post those problems for you so you don't have an issue.
Okay.
But maybe one of your classmates can give you some guidance.
Yeah.
I mean, because what I see on my end as an instructor is completely different than what you see, so I don't know what are the motions on your end.
Yeah.
All right.